Hello and welcome back to Mrs. Ogram's Maths. Today we are taking a look at Level 3 Algebra and Complex Numbers for the Calculus Externals. We are looking particularly at the achieved merit sections of this. So that's the first parts of questions 1, 2 and 3. Part A and B are always achieved points and Part C is merit. Now they can change that order up a little bit in the external, so just be aware of that, but it's usually in that order. So we're going to focus on that first half, getting you through to being really confident with some parallel questions for achieved, and then having a go at being able to get that little bit more and come away with a merit. All right, so getting stuck in with question 1. Find the values of k so that this particular expression has exactly one solution. So if we're talking about nature of roots and number of solutions, we are discussing the discriminant, which is b squared minus 4ac. If there's exactly one root or one solution, that means that that discriminant is equal to 0. B in our equation here is the bit that goes with the x, so we need to square that whole thing like so. A is a 1 at the front here, and C is the k at the end there. And we need to set that equal to 0. Now we're going to go through and solve that, so that becomes 16k squared minus 4k is equal to 0. We can take out a factor of 4k and we end up with 4k minus 1 in the bracket. So from this part of that multiplication we end up with k equals 0, or from this bracket, if we set 4k minus 1 equal to 0, we would get 4k is equal to 1, k is equal to a quarter, so k equals a quarter. For part B, we've got the complex numbers u and v, and the multiplication of the two is equal to this. And we want to find the value of b just here. So to find v, we will do uv divided by u, or minus 54 minus 12i divided by 12 minus 3i. So I'm going to go over to the calculator, and we'll put in negative 54 minus 12, and then to get the I we use our options, complex, and there's the I, and we'll divide it by 12 minus 3I. So that equals minus 4 minus 2i, and just matching up with what we've got as v over there, we can then say b is equal to minus 2. Okay, solve this equation for x in terms of h. So we are on part C, which means it's worth a merit point. If you get part way through these ones, it'll be worth an achieved, and then if you get all the way through, it'll be merit. Okay, so the reason they have an h in here is so you can't just do all of it on the calculator. You need to show some further thinking to be able to get those merit points. Okay, so we want to try solve this out. Just pretend that h isn't there for now. Treat it as if it's a number, you just don't know what that number is. What would you do to find out x? So we would square both sides. And there's the expansion of that right-hand side. And then go about rearranging it for x. So we've got a 16x on that side that cancels with that 16x. So then we can take over the 100 to that side would be equal to negative 80 root x. I'm just going to switch those over just to make it a little easier to deal with. So then root x is equal to 100 minus h over 80, and x will be that thing squared, like so. All right, question 2, let's keep going. So we've got the modulus of this complex number here is equal to 15. What could r be? So modulus is when you do the square root of the 9 squared from this bit and the negative 4r here from that bit. So 9 squared plus negative 4r squared, and then you square root it, will make 15. So 81 plus 16r squared will be equal to 15 squared, which is 225. So 16r squared is equal to 225 minus 81. Okay, let's divide that by the 16. R squared is 9, so r is plus or minus 3. If x minus 2 is a factor of this expression here, then we can find out the value of k. So let's call that function f of x. So if we put 2 in, it will give us an answer equal to 0 because x minus 2 is a factor. So that's using the factor theorem. So f of 2, oh, that's bad writing. There we go. F of 2 is 2 times 2 cubed minus 3 times 2 squared plus k times 2 plus 6, and that will come to 0. What we get from that is 2k plus 10 equals 0. So 2k is minus 10, k is minus 5. Right, part C, another merit one. So 2 plus I is a solution to this equation that we have here. Find the other solutions and also the value of k. So if 2 plus I is a solution, 2 minus I is also a solution because of the conjugate root theorem. So if you have a complex root, its conjugate is also a root. And then x minus each of the roots are factors, so we can multiply them together and find another factor of this expression. So expanding looks like this, and then we'll simplify, coming to x squared minus 4x plus 5. So we've got x squared minus 4x plus 5 is a factor of that original thing. We'll have something x plus something. If we multiplied that out, will give us, oh, I've just realized I've done everything in x's when it should have been z's. I won't go back and change the work above, but we'll carry on with z now. So this thing here that we just worked out, multiplying out the factors, would get times by another factor to make this be true. So let's see what needs to be there. So to make a 2 in front of the z cubed here, we would need this 2 in front of the z here. So when they times together, you'd get the 2z cubed. Then consider the final part here. So we've got a 5 at the end. Whatever number goes here would need to times by that 5 here to make this 5 here. So of course that is just 1. So we've got 2z plus 1 will be that solution. So the third solution is from this bracket here. Setting that bracket equal to 0 gives us z equals minus a half as our third solution. And finally, the value of k up here. So this bit just here, we can work on expanding through to work out what that needs to be. So we only need to consider the bits that make z squared when we times it out. So we've got minus 4z times by 2z is minus 8z. Oops, z. The other way we could get a z squared is from this multiplication here. So plus z squared would equal the kz squared in our expression. So minus 8 plus 1 is minus 7, so k is equal to negative 7. Okay, question 3. Show this is true, so let's start by doing the modulus of s squared. Now you can use your calculator to do modulus. It's this ABS, meaning absolute. So the absolute value of 4 plus 2i is equal to this much, and then if we square it, we get 20. Modulus of w squared, absolute value of w is 1 minus I, and square that is equal to 2. 10 w modulus w squared would then be equal to 20. Therefore, modulus of s squared is equal to 10 times the modulus of w squared. Okay, part B, we want to do u over v in polar form. That means we divide the modulus, so 3k to the 5 over k squared, cis, and if we're dividing, we subtract the arguments. So that becomes 3k cubed cis of 3 pi by 4. 1 minus quarter is 3/4. And finally, the last chance for merit on these ones, part C, show that this is a real number. Okay, so the modulus of z squared is the square root of a squared plus b squared. So the modulus of z all squared would be a squared plus b squared. That's real at the moment. Z times by its conjugate is a plus bi times by a minus bi, and if we expand that, we get a squared plus abi minus abi minus b squared I squared. So those middle bits cancel. I squared becomes minus 1. We get a squared plus b squared. So then that is also real. The modulus of z squared over z conjugate is equal to a squared plus b squared over a squared plus b squared, which is 1. Therefore, it's real.